So reaction mechanism 15 is a reversal of what we saw in 14. And again, what we saw in 14 was aldol addition chemistry, or carbon-carbon bond making. Now we're going to be doing carbon-carbon bond breaking. So again, sometimes this chemistry is difficult to spot because we're not necessarily looking for something that's nucleophilic as part of one molecule to attack something that's electrophilic and another one kind of in combining chemistry. Now we're looking for how to break things apart. So we have to find bonds that are what we call labile or easily broken. So how do you find things that we can do chemistry with that we can be breaking apart? Again, carbonyl containing functional groups. So carbonyl containing functional groups like aldehydes, ketones, so forth. Look at the alpha and the beta positions for chemical options. So again, carbon atoms that are alpha 2, that is immediately adjacent to carbonyls, are going to have hydrogen atoms that are acidic, right? That's how we make them nucleophilic. Again, that's how we get to this product in the first place in reaction mechanism 14, is we deprotonated at that alpha carbon, generating our nucleophile that we could react with another carbonyl containing compound that was our electrophile. So thinking about this in the reverse process, we can easily break a bond between those alpha and beta carbons because we're going to be generating that resonance stabilized intermediate. Again, this is going to be chemistry that becomes really important later when we talk about getting rid of, getting rid of carbon dioxide from fuel molecules. And we'll revisit this in our applications after we do the mechanism. Again, so looking for heteroatoms at the beta position to a carbonyl. Again, in the molecule that we're going to talk about here, this is a beta hydroxyketone, so it's going to be an alcohol functional group. That's going to be important starting points for chemistry. And again, this is going to be the reversal of the mechanism that we just did. So what we're really going to be able to do is reverse earlier steps, but also that means reversing the kinds of chemistry that we're doing. So doing protonation events when we saw deprotonation in the forward direction. So let's go ahead and start out this mechanism and see if it all makes sense here. So I'm going to start with the beta hydroxyketone. So I'm going to draw my beta position here. And for reasons you'll see in a minute, I'm going to draw out that hydroxyl group showing my bond here. Here's my alpha carbon. And then I've got a ketone, so that group must be an R. So again, I'm just going to go through and label what we can see here. This carbon is the alpha carbon because it is immediately adjacent to the carbonyl. This is the beta carbon. And so the bond that we're referring to as being labile is this bond right here. So again, this is going to be our labile bond. Our bond that's easily broken. So how we're going to start out this mechanism is we're going to have a base come in and deprotonate this alcohol group. Deprotonating that alcohol group is going to generate this intermediate here. And now we have the ability of sort of doing the reverse of our kind of carbon-carbon formation step that we saw in our last mechanism. And we're going to regenerate our carbonyl on our species on the left here, breaking this labile bond and generating, or regenerating in this case, an aldehyde. And then again, with these carbon-carbon bond forming or breaking reactions, keep atoms in sort of their original positions, and that sort of helps make sure that we don't lose anybody. So again, why this chemistry is important is I'm going to show a resonance structure here. So I'm going to use arrows like that. I can take these electrons here, don't forget my negative charge. These electrons can be delocalized and stabilized through that carbonyl carbon. And we've talked about in previous mechanisms why putting those electrons on that oxygen would probably be better because that is a more electronegative atom, and so it's going to be better able to kind of stabilize that charge that we have there. So again, that resonance stabilized enolate is going to make it a good leaving group. So again, we've got a resonance stabilized enolate. And essentially, anytime we're breaking a bond here, we're asking these electrons to go and reside on a certain carbon and generate an anionic intermediate. So just like we see if we're deprotonating something and you're generating a conjugate base, anytime you can have something that's negatively charged and is stabilized in some way, it's going to be better able to handle that negative charge, so it'll make it, again, a better conjugate base if you're talking about acidity. In this case, it makes it a better leaving group. Better leaving group means that's a more labile bond, more easily broken. So again, if we take and consider just finishing out this mechanism here, we're going to have a base here, an acid that we can consider reprotonating, our enolate intermediate, and we're going to get back to our ketone here. So a couple of things just to kind of highlight here as I've seen mechanisms from you guys over the past few weeks here. When you're drawing species that are going to be acting as, in this case, bases, and in this case as acid, you always want to make sure that you're consistent within your mechanisms. So if your base is not showing any charge, your acidic species should have a charge of +1. If you'd like to show this guy as neutral, then this guy must have a negative charge. So however you want to do it is fine. You just need to make sure that you're consistent. And just making sure to highlight how this all works here, right? When these electrons come down and reform our pi bond right here, these pi electrons form a sigma bond to that hydrogen, and so that's that hydrogen that's there. So we really end up putting that hydrogen atom on that carbon, which is why we get a CH2 group there. So hopefully that mechanism was not too squirrely for you. Hopefully it was okay to kind of watch and see how that kind of played out. Lots of comments here that I kind of want to talk about, and then again discuss the context. So again, one thing to notice here is that when we have a heteroatom at the beta position, we have unique possibilities for chemistry. So again, just flipping back here, this is the heteroatom that we're talking about being on this beta carbon. So having that heteroatom allows us to deprotonate this alcohol here, generating this species, which we can then reform our carbonyl and break that bond. So again, here we're using that chemistry to break a carbon-carbon bond between our alpha and our beta carbons. Again, we didn't see this chemistry when we had a heteroatom at the alpha carbon. So again, just flipping back here for a second, remember when we had our OH group at this position? Reaction mechanisms 8 and 9 allowed us to walk our carbonyl between two adjacent carbon atoms. And that's because we could deprotonate the hydrogen on this alpha carbon, and we could then walk that carbonyl around. So that's different kinds of chemistry. We didn't do anything with deprotonating this alpha carbon's hydrogen here. And largely that's just because that's not the direction that we needed to go to get to our product here, which was to break a carbon-carbon bond. So again, we're going to see that heteroatoms, right, play extremely important roles in lots of chemistry with metabolism. So what's interesting is when you start with fuels like carbohydrates, which carbohydrates are carbon, hydrogen, and oxygen, they already have that heteroatom present. But when we think about fuels like lipids, which are largely hydrocarbon, we actually need to do some oxidative chemistry to introduce those oxygen atoms. And that's some really interesting biochemistry we'll talk about in Biochem 2 when we learn about lipid breakdown. So again, applications that we're going to talk about here. Again, these are really the only two mechanisms that we're going to talk about right now that have to do with either carbon-carbon bond breaking or making chemistries. So again, this is an important carbon-carbon bond breaking chemistry. Again, lots of time at the end of this semester and all through next semester discussing fuel metabolism as catabolic processes, so breaking bonds. Again, most fuels, carbs, proteins, lipids are very carbon-carbon bond rich. This is going to be chemistry that's really important to understand. So the first time we're going to encounter this chemistry is right at the beginning of Biochem 2 when we study the details of glycolysis and talk about the carbon-carbon bond breakage that occurs with fructose 1,6-bisphosphate. And so basically we take that 6-carbon sugar and we break it into 2 3-carbon pieces. We're going to refer to them as glyceraldehyde 3-phosphate and dihydroxyaldehyde or dihydroxyacetone phosphate. So again, if you've studied these metabolic processes already, maybe you've talked about GAP and DHAP. This is step 4 of glycolysis. This chemistry was, again, a reverse aldol, so not surprising when this enzyme was named in a more historical context. It was named aldolase because of that kind of chemistry, that reverse aldol addition reaction. So again, we're also going to see a good deal of carbon-carbon bond breakage chemistry when we talk about decarboxylation reactions, that is losing carbon dioxide. Remember our fuel equation, right? Fuel plus oxygen gives carbon dioxide, water, and energy. So thinking about how we generate that carbon dioxide, how we lose CO2, a lot of that we're going to see is through carbon-carbon bond breakage chemistry, and most of it is going to be through these decarboxylation reactions. So lots of important chemistry that we're going to see both from reaction mechanism 14, where we're making carbon-carbon bonds, but really importantly with reaction mechanism 15, when we're breaking bonds.